All right, let's start. So welcome to the Budapest AI Meetup. I'm your uploader, and we're gonna have 3 presentations today. And the very first one is Zoltán Tősér from ARGUS community.
Thank you, Zoltán. Thanks for the introduction. You guys can't see my slides yet. Let's wait for those. Okay. All right. So the topic of today's talk is when AI applications are deployed in the real world, and people have really high expectations of levels, and then some problems happen, which I label as an event when reality hits. So before we go into the details, let me tell you a few words about myself. I'm the CEO of ARGUS Cognitive. We founded this company a few years ago in the US. Our primary business is AI-based medical decision support software development. So what does this mean? It means that we see a problem where clinicians, doctors have an access to a huge amount of data and don't know what to do with that. And at the same time, they are so overwhelmed with work that they just cannot tackle dealing with all the patients. So clearly there's a problem there. And what we're trying to do is aiding them with AI-based tools in pre-filtering, for example, or quantification of behaviors or some other health characteristics, quantifying this information, providing them reports in order to make their lives easier, to help selecting the patients who really need an experienced doctor's attention, or selecting the ones who can be dealt with by someone who is not that highly qualified. Right. We have 2 products in development. Actually, these are late development products, so we don't do much tweaking of the systems now. We are just fighting with the regulatory authorities to get these systems approved. One of the systems, I would say this is our flagship product. It's a tool for measuring or quantifying autism symptoms. So what does this mean? The state-of-the-art way that autism nowadays is monitored and diagnosed is basically a clinician sitting in a room with the patient, and it's just some natural interaction, verbal and non-verbal, and the clinician is taking some notes on a sheet of paper. So that's not that high tech. And what's wrong with that? So the doctor's attention is split between looking at the patient, writing down the notes, and evaluating all this and conducting the experiment itself. So that's too much, and that's one problem. The other problem is that it's really subjective. So one of the components of this gold standard test for diagnosing autism is it's about the quality of eye contacts. So you can imagine how different people measure these differently, right? So if an eye contact looks normal to me, it may mean something totally else to a different person. And even though this is more or less standardized to some extent, it varies considerably between clinicians. So this tool we are developing takes care of these subjective variants in the data. And the the value we deliver, the product, the core of the product itself is a report, detailing all the relevant behaviors, how many eye contacts were there, what were the gestures like, what was the body talk, what were the different acoustic parameters of the speech. So we really try to cover the whole behavior spectrum. That's the first step. That's not that useful in itself because, in imagining yourself into the place of a doctor, who would want to deal with a long list of numbers, right? As a second step, what we have also done is we compressed this long list into a single score. That it doesn't give you such a detailed insight into the behavior of the patient, but it's enough to get a general quick overview if this patient really is problematic or what's the overall progress. So I would say that's the main thing, creating this single score to help the doctor. We started the company with this product, and we soon realized that even though we are more or less specialized for autism and for other mental disorders, we can use the underlying algorithms for other types of clinical domains. For example, we ventured over to cardiology, which of course has nothing to do with autism, but the underlying algorithms are the same. We have the knowledge and the manpower to create such systems. So we just said, why not? Let's see how it goes. So this other type of system, which by the way, you can't really see because it's too dark. It's a right ventricle. That's one cardiac chamber in the heart. That system is just about characterizing the different movement the right ventricle does in a more detailed manner than it was previously possible. So the root of the problem there is that the conventional parameters do not give us a deep enough insight. So doctors can't really decide if a patient is, it's really at risk or not. About 40% of people with right ventricle failures do not show anything out of range in the normal right ventricle cardiac parameters. So that's something we have changed, and we are just in the middle of getting these two systems approved and getting it out to users. So that's about what we do and who we are. The way I say AI in these past few years, of course, there has been this big boom around 2015, 2016, and things, there are a few success stories. For example, speech recognition, right? I mean, it's solved. It's here in my pocket on my phone. It's working well enough to create even applications in the medical domain using this technology. So I would say that turned out well. In other domains, for example, with self-driving cars, that's it's ready-ish. I mean, there are systems like this deployed out there in the roads. For example, we have Waymos, Tesla cars driving themselves. But there are some well-known problems with these systems. For example, they don't really handle different weather conditions well. That's why they test all these in the southern states in the US and not up there in Canada. Some companies are trying to change this, by the way, and they have set up some testing tracks in Norway or Finland, I think, so up in one of the northern countries. But it's not there yet. So that's why I label these as emerging fields. And as for healthcare, well, I have seen many promising, startups and their AI-based healthcare applications. More than I can count, but where are these? I mean, I've seen pitches of these. I've seen these in conferences. The healthcare conferences, by the way, are all about AI nowadays. But you know, when I go to the doctor, I am not diagnosed with this system. So, and that's not a problem specific to Hungary. It doesn't really work that way in the US either. So there are these applications. Why aren't these all around the place in the hospital? And of course, I'm exaggerating a bit because there are some few examples, but you know, these are rather exceptions than the rule itself. So I think you know, in order to get a healthcare system out there and get some people to use it, from development until there are actual users, this takes more or less about 10 years. That's the rule of thumb. So if the whole process takes 10 years, I mean, you know, AI algorithms change every few months. So how can you stay on top of all this if you need to constantly tweak and update your system? And as far as I see, no one has figured this problem out. So the way it happens so slowly, because you know, you always need to keep updating your system because the algorithms are developing at such rapid pace. And of course, in order to get these approved, that also takes quite a lot of time. You know, changing users' behavior, that's, I think most of you are familiar with this. I mean, if they have kept doing something for I don't know, 15 years or 20 years, you can just expect them to believe that your latest fad works so much better than all the previous stuff, and you know, expect them to keep getting jump on the latest and latest stuff. So that also takes a considerable time. And as I said, it's about 10 years. So that's why these applications aren't out there. And you know, it's not just the regulatory environment and not just the acceptance rate or the pace of acceptance for the users, but even the development itself is slower than people see it in other domains. And part of the reasons is that in the healthcare, most domains, most applications do not have a significant amount of data. So the three pillars of modern AI, of course, I think most of you know this. It's access to a lot of data, it's hardware, and the algorithmic breakthroughs. These three things are the things that have allowed this AI revolution, I would say, in the past few years. But in healthcare, even though some disorders have tremendous amount of data, I wouldn't say this is typical. Most researchers just mess around with, I don't know, hundreds or maybe thousands of data points. And how does this compare to hundreds of thousands of images used in other applications? So that's one part of the problem. And in order to ensure that this data has a sufficiently high quality, you know, people just record these under ideal lab conditions and not in the real world itself. And of course, because they understand their data well, know what corner cases there are, what exceptions there might be, when they try to deploy their systems in real environments to real users, that's where reality hits. So let's see a few examples of what does it mean when reality hits you in the face. So one of the typical application types in mental disorders, I would say, goes like the patient is sitting in front of a computer screen, and there is some test going on, and a camera on top of the screen which is recording the patient, and you know, the system measures various stuff. So that sounds good in theory, but you know, when people go ahead and create such a system, and the patient sits in front of the screen, and you know, someone else, this other guy appears, and who is this even? Like, is this the parent? I don't know, but the system successfully managed to track the patient. I mean the parent itself of the patient. So, you know, and this was never like this in the training data. We wouldn't have foreseen this. Okay, so what other examples are there? So let's say we have multiple people around the room, and let's say we can recognize who is the patient because we have learned from our previous mistakes. And you know, we see that there are a few people around. We detect that one of them is the patient because, I don't know, because of the facial appearance, because he looks young. And we would expect that the system would work now, right? So, no, reality hits back. So, what's this? Is that a window? Well, that's a mirror. And, you know, there's a kid's reflection, the patient's reflection is in the mirror. But the problem is, well, where's the kid? Of course, it's the kid is in front of the clinician, but we can't see her. So how do you solve such a problem if you have never seen anything like this in the training data? It's a significant problem in most applications, I would say. And, you know, to those of you who have kids, well, they can get really creative at breaking things and pushing the limits of various systems. I think many of you are familiar with these. For example, in the case of speech analysis, people do not expect when developing a speech analyzer that there would be a TV in the background, right? So one of the best speech analysis companies who specializes for autism had to do a separate background TV noise classifier, right? So, and you know, it's just that was one problem, but there are countless others. For example, in one of our experiments, we've seen that the kid just simply hid under a blanket and disappeared from the recording. So, you know, our system was prepared for tracking the kid and managing if he gets out of the screen or if someone is in front of him. But, you know, with this blanket, we saw that the kid just appears and disappears. So yeah, kids can get creative. Also, well, you know, we tested with young kids with short hair or with the hair in a ponytail. But you know, in the real world, when you put this application out, some kids just couldn't bear, you know, having their hair in a ponytail. So hair just covers all their face, which is really good for facial expression analysis, I can tell you. Okay, so there are some really problematic problems in this healthcare domain, but is this just healthcare? And hell no, it happens all the time, everywhere. 1 month ago, Andrej Karpathy and Elon Musk delivered a speech on a Tesla conference about the latest stage of their self-driving car development. And you know, they have really good detectors. They can detect where the cars are, where the other people are, where are the cyclists, where are the traffic signs, and you know, and I mean, it's really good. I mean, they essentially built an almost perfect car detector and bicycle detector. Okay, what the hell is that? So yeah, this is when reality hits. People actually attach bikes to the back of their cars, and if the system successfully detects this as a bike, and because it looks as if it were going to the left, you can imagine how many false positive alarms this has caused in the Tesla systems. Right, and up until this point, we haven't really talked about any malevolent intent or any attackers. This was just, you know, just the real world doing its job, being the real world and providing these amazing failure cases. But about 2 months ago, a research paper came out from a Chinese company, and they analyzed the fullability aspects of Tesla's self-driving car. And you know, those 3 little marks encircled in the top right corner, those are some signs prepared by these Chinese attackers, laid over the road. They are not that visible. I mean, I can see it from here that there are some blurry pixels there, but that's it. You can't really recognize them. But the thing is, these 3 little dots managed to navigate the Tesla into the oncoming traffic. And of course, no people were harmed, etc., because this was a simulated environment. But you know, those 3 little dots, that's enough to make the Tesla think that there's a lane change coming. So that's a more serious problem, I would say. And just as kids, people can and people will get creative, and they will figure out ways to fool these systems. Okay, why don't we foresee these problems? I mean, we are not stupid. We are familiar with the training data. We know what it looks like. We have such a huge amount of background as human beings, but you know, some of this knowledge we have, this really came from evolution over I don't know how many years, hundreds of thousands of years, and or maybe more. So we understand physics really well. We understand that there are laws of conservation. If something is moving and there are no external forces applied to this stuff, then even if I don't see this object, I can assume that it will keep moving. This type of knowledge is not present in these AI-based models yet. And even understanding the 3D space itself. So nowadays we have some good depth estimator systems, but you know, we are not that sure that this is the same type of understanding of the 3D space that we humans have. Even though that you know, these systems work well on benchmarks, it's a different story how they work in real life. Also, one of the examples we've seen before, reflections. I have not seen a single system yet that can manage reflections. This may be a problem in rooms, and this was one of the examples before. But you know, just imagine dense urban environments with all these skyscrapers, all the glass on their sides. So you know, the system probably has some built-in fail-safes to not navigate based on the reflective images. But you know, taking away these hard-coded rules, it doesn't understand that that's a reflection, so that it has to be reflected off something. But we humans do understand this, right? Also, the so-called Gestalt principles of grouping. There are many of such rules. One of them is that if things move together, then they belong together. So, for example, this image with the bike attached to the car, those things move together at exactly the same pace, and you know, they turn at the same time. So we humans assume from experience, or you know, or from our inherited knowledge, that they must belong together. So it's somehow that the bike is attached to the car. And even though we have never seen such an example before, maybe, we understand that it's not a separate bike crossing the street. And of course, we have an immense knowledge about the cultural environment we live in. One of the behaviors our psychologist partners asked us to develop for the autism product was the so-called delayed echolalia. So what's that? Echolalia is when a kid is repeating something. So I don't know, you tell him or her a word and he just keeps repeating that. A delayed echolalia is when the kid heard this in the past, let's say a few days ago, and he just it ticks in, and the kid starts repeating it. Let's say the kid saw a cartoon intro 2 days ago. How do you realize that it must be some cartoon intro that the kid is repeating over and over again? Well, maybe because you're familiar with what shows the kids watch, right? If you're a parent. But the speech analysis system cannot really do that yet. This is a Google level task right there. So these are the problems, and how do we solve these? Well, the thing is, I have some bad news. There is no silver bullet. There is no uniform solution that can solve all these types of problems. The most I can give you is some general guidelines to use in developing these products. So first and foremost, you need to detect when the system does not work, right? And how do you do that? So first of all, you have these assumptions about the system. If you remember, we had an example